Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiren Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to cover classes and the need for encapsulation. Now, in this topic, we will first discuss the need for restricting access to member variables, and we will see how the compiler can help with overcoming the additional costs such restrictions make. We will see how making all member variables private prevents future changes to your class from harming your existing user base. And we will finally define the idea of an interface to a class. Now, let us review the 3D vector class we previously authored. It has three member variables, x, y, and z. So, wouldn't it be easier just to leave these public and just call them x, y, and z to make it easier for the user to use? After all, the underscore is not really that useful, and there are no restrictions on any of these three values. There's no real value that the user could set to any of these member variables and not have it represent an actual three-dimensional vector. So consequently, what would be the benefit of having encapsulation? So for example, why would you bother wasting your time to make x, y, and z member variables private and then introducing functions that both access and allow the user to change the values of these three private member variables? Well, one problem is you are not clairvoyant. That is, you cannot predict the future. However, if you can, do call me about next week's lotto numbers, please. Anyway, so once users are accessing your member variables, you're now constrained. You can no longer change your underlying design of the class. For after all, if they are using your member variables and then you change one of them to mean something else or just take it out altogether, then you're going to break someone's code. If you break someone's code with an update to your class, someone's not going to be very happy. So suppose we do it the hard way. That is, every time the user wants to access a member variable, the user must call the appropriate member function. That seems expensive because you already know how much work is required in a function call. All the information that must be put on the stack, and then the return value must be placed back onto the stack and then retrieved and then used. Well, actually, that's not really true. Compilers these days are very good at optimizing code. Specifically, one thing compilers can do is look at a very short function and notice that it may actually be easier to remove the function call and instead replace it with code that achieves exactly what that function call would have done in its place. So if all you're doing is accessing a member variable which is being returned by a function, the compiler can simply decide to replace that function call with just access to that member variable's value. So it's not that bad an idea to have an interface like this. And it's not that much work, and the compiler can ensure that under certain circumstances, it doesn't even affect the runtime. Now, one thing that's nice about encapsulation is suppose in a few months after you introduce this class with three member variables x, y, and z, you suddenly determine it's better to just have an array of capacity 3 instead of three separate member variables. Now, if all of your users were accessing member variables x, y, and z, Changing these three member variables into a single array would break all of their code. This is not going to make your users happy. However, if all you do is change the underlying representation to an array, and if all your users were simply calling member functions anyway, then you simply have to update how these member functions work. So, for example, here I have replaced the three member variables x, y, and z with a single array, which I'm calling x, y, and z, of capacity 3. Now the constructor just initializes that array, and the member functions x, y, and z that return the corresponding entries now simply return the corresponding index into that particular array. Similarly, the functions x, y, and z that allow the user to set a value simply set the appropriate entry of that array. The user might not even notice that a change was made because all the functions behave exactly the same. Now, spherical coordinates are something that you are going to learn about in second year. However, every single point in R3 can be described by the radius, the inclination, and the azimuth. And through these three values, every single point in R3 can be uniquely identified. These are useful in certain applications and are often more useful than, say, rectangular coordinates x, y, and z. Thus, let us assume we are adding additional member functions that return the spherical coordinates of this point in R3, that is the radius, the inclination, and the azimuth. We can either access each of those coordinates or we can change each of those coordinates. Now, to help us in changing those coordinates, we're also going to introduce a new private member function that converts the spherical coordinates r, theta, and phi into our rectangular coordinates. Thus, we can implement the three accessors, that is, the three functions that return the spherical coordinates, simply by looking up the appropriate formula in a textbook. Notice, interestingly enough, the second, the inclination, actually has a call to the first, the radius. Also at the bottom is our private member function that converts the arguments that represent the spherical coordinates of a new point and stores or updates the x, y, and z to reflect these new coordinates. Thus, we can implement the functions that update the spherical coordinates by simply retrieving the current spherical coordinates for the other two and replacing the new one and converting those three to rectangular coordinates, which will update x, y, and z appropriately. Now, your three-dimensional vector class is being used more and more in your company. However, on reviewing how your class is being used, you learn that more and more calculations simply require spherical coordinates and not the rectangular coordinates. Well, if that's the case, it would be nice to actually replace the member variables. But if the member variables are all public, there's nothing you can do. However, if all your member variables are private, then all you have to do is change them and rewrite the member functions that access those. And from a compilation point of view, no one will notice. If their code compiled before, it will continue to compile. Only what is being compiled may change slightly. Notice that if we take out x, y, and z and replace it with r, theta, and phi, the user doesn't notice. There's been no change to the member functions that the user can call. The only thing that we will change is instead of having a 2 rectangular coordinate function, we will have a 2 spherical coordinate function given rectangular coordinates x, y, and z. Now we can update our implementation. Now, one interesting point is one function that everyone has been using is the constructor. And the constructor assumed that the arguments were the x, y, and z coordinates. We have to leave it this way because users have already been using it. So consequently, we would initialize r, theta, and phi based on the rectangular coordinates of the arguments. Now, what happens if someone wants to create a new vector with just 3 spherical coordinates? Well, this is also possible with something called a factory method, but we'll discuss that later. Right now, we cannot change the constructor because everyone has already been using it under the assumption the 3 arguments are the rectangular coordinates of the object. As far as x, y, and z, again, now we calculate the values of these coordinates based on the spherical coordinates. One thing I'd like to point out is notice that the first value that's assigned is r, the radius. Notice that the second one, when we calculate theta, we are actually using the first member variable. That's actually okay because these are guaranteed to be assigned in the order in which they appear in the class definition, and we made sure that we wrote them down here in that same order. So we're guaranteed that the radius is calculated first, then in calculating the inclination, we can use that radius member function, and so on and so forth. Now, to update any of the rectangular coordinates, all we have to do is take that new coordinate, which is of course the new x, y, or z value, and the 2 other current values in rectangular coordinates, and we will call our new private member function toSpherical, which will update the member variables r, theta, and phi to correspond to the new rectangular coordinate that we have just updated. Now, retrieving the 3 spherical coordinates all of a sudden became a lot easier. Now, here we see 3 functions to update the spherical coordinate member variables. However, in order to have a normal form, we require that the radius is greater than or equal to 0, the inclination is between 0 and pi inclusive, and the azimuth is greater than or equal to 0 while still being less than 2 pi. So in this case, we have simply decided to throw domain error exceptions if the value passed by the user doesn't fall into these categories. However, on the other hand, this isn't the only solution. You must remember that spherical coordinates are periodic. Consequently, it would not be hard to map an inclination back to the interval from 0 to pi. Or if the radius is negative, we could change the radius to being positive while updating the azimuth and inclination to be in the opposite direction. But that's way beyond the scope of this course, but something for you to think about. Do you want to throw an exception, or do you compensate for perhaps an error or something that users should actually be allowed to do? But that's just for thought. Don't worry about it for this course. Now, to be honest, the scenario we're presenting is not very likely. But what we want to do is make you recognize the usefulness of restricting access to member variables, even if initially it seems unnecessary or burdensome. Also remember that if a function is very short, the compiler may simply decide to inline that function, meaning it will actually replace that function call with equivalent code that performs exactly what that function call would have done. Consequently, having a lot of small function calls for specific member functions may not actually affect the runtime whatsoever. And also to introduce a new term, another term that describes the collection of all member functions that allows the user to access and manipulate an instance of a class is the interface for that class. That is, this is how the user works with and interfaces with your particular class as you have designed it. So following this topic, you now understand the need for encapsulation, specifically the need to prevent users from accessing the member variables of your class. You also know that you will now be having all your users access and manipulate your class, including its member variables, through member functions. However, you also know that the compiler will help ameliorate the potential impact of having all these additional member function calls through a concept called inlining. You also know that another term for all member functions that allow one to access and manipulate a class as being the interface to that class. Here are the references, the colophon, and a disclaimer. Cheers!